What exists outside the observable universe? The Big Bang took place 13.8 billion years ago, and the cosmos we live in was created. The cosmos was hot, dense, expanding, and made out of matter, radiation, and antimatter. There is a cosmic limit to how far we can see, despite the fact that it has been billions of years since the Big Bang. All this time, the cosmos has been expanding, but the pace of growth is limited and can be precisely measured by us. The maximum distance we can see in one direction, according to calculations of how far a photon from the Big Bang may have traveled by the present, is 46 billion light years. We refer to it as the observable universe. But what is there that cannot be seen? What about the universe that is not visible? We cannot even think about something we cannot see. All of these and more will be discussed in this video. But only if it were that simple to respond. Currently, the universe is chilly and clumpy, but it is also expanding and gravitating. Due to the finite speed of light, when we stare farther and farther out, we not only view far off in space, but also look back in time. Larger, more complex structures that take longer for gravity's effects to manifest themselves are more and more uniform, less clumpy, and take less time to form in the more distant universe. It was quite hot in the early universe. The early universe was opaque for roughly 300,000 years because it was so dense that not even light could pass through it. But gradually, the universe started to become transparent. The wavelength of all the light traveling through the universe is being stretched by its expansion. Stretching a wavelength causes it to lose energy and cool down. This is why redshift, the term for the color change that occurs in light as it moves through the expanding universe, occurs. The universe was hotter in the distant past, according to this observation. By merely observing the lingering radiation from the dense and intense early stage, we may determine the temperature of the universe as it is today, 13.8 billion years after the Big Bang. Cosmic microwave background radiation, or CMB, is the name given to this radiation in modern times. The precise proof of the Big Bang theory provided by the cosmos microwave emissions makes them a crucial piece of evidence for the model. They have a temperature of 2.7 K and a blackbody spectrum. But it's crucial to note that as the universe expands, this cosmic microwave radiation changes in energy. The energy of a photon is inversely related to its wavelength. The Big Bang's photons had twice as much energy when the universe was half its current size, and 10 times as much energy when it was just 10% of its current size. The universe was 1,089 times hotter than it is now, or about 3,000 K, if we are willing to travel back in time to when it was only 0.092% of its current size. The universe can ionize all of its atoms at this temperature. The early universe was hot, dense, and in the form of an ionized plasma, as was already mentioned. It was impossible for light to elude this early universe. But you might be wondering how we arrived to the current universe's size. But if we want to see beyond the observable universe, the size of the cosmos is crucial. When we think about the extent of the cosmos, we often consider three things simultaneously. 1. The current rate of expansion of the universe, which can be determined using a variety of techniques. 2. The current temperature of the universe, which can be determined by observing the cosmic microwave background radiation. 3. The components of the universe, such as matter, radiation, neutrinos, antimatter, dark energy, and more. We may extrapolate the hot Big Bang's early stages and calculate the universe's age and size by keeping these three crucial factors in mind. We learn about the cosmos from all of the observations that are currently possible, such as the cosmic microwave background as well as information from supernovae, extensive structure investigations, and acoustic baryonic oscillations. Its radius has grown to 46.1 billion light years as of 13.8 billion years after the Big Bang. The observable is limited to that point. Even further away, something that has been traveling at the speed of light ever since the fiery Big Bang won't have had enough time to reach us. The universe will become older and bigger over time, but our ability to witness everything will always be constrained. What can we say about the area of the cosmos outside the range of our observations, then? Only the things we can measure in our observable universe and the principles of physics as we currently understand them allow us to draw conclusions. With an accuracy of 0.25%, we may say, for instance, that the cosmos is spatially flat on the biggest scales and neither positively nor negatively curved. We can at least constrain the size of the universe before it collapses back on itself if we assume that the current laws of physics are accurate. The finest information comes from observations made by the Planck satellite and the Sloan Digital Sky Project. They claim that as the cosmos closes in on itself and curves inward, the portion that is visible is identical to not curved in the sense that its radius is at least 250 times greater. Thus, the unobservable universe must have a diameter of at least 23 trillion light-years and a volume of space that is more than 15 million times larger than what we can see, assuming there is no topological insanity. Yet, if we are ready to make a wild guess, we can make a compelling case that the unobservable cosmos should be far larger. We may determine the future limit of visibility, or the greatest distance we are able to observe, based on the rate of expansion, the amount of dark energy we have, and the existing cosmological parameters of the universe. Our current sight limit in a universe 13.8 billion years old is 46 billion light-years. Our potential visibility limit is 61 billion light-years, which is approximately 33% greater. There are galaxies whose light is currently traveling towards our eyes, but has not yet had a chance to get there. We would be shocked to realize that there are more undiscovered galaxies than there are visible galaxies if we added up all the galaxies in the regions of the cosmos that we will one day observe but cannot access right now. In addition to the 2 billion galaxies we presently have access to, there are another 2.7 billion galaxies waiting to illuminate us. We currently only see 43% of the galaxies that we will one day be able to observe, compared to what the future contains. The unobservable realm, which lies beyond our observable reality, ought to resemble our observable universe in every way. This has been confirmed by observations of the cosmic microwave background and the universe's large-scale structure. The observable universe as we know it may have begun with the hot Big Bang, but space and time did not begin with it. The universe had a period of cosmic inflation before the Big Bang. The universe was not hot or full of matter and radiation, rather, it was full of the energy that comes from space itself, expanding at a constant, exponential rate, and creating new space at such a rate that the Planck length, the shortest physical length scale, would be stretched to the size of the currently observable universe every 10 to 32 seconds. It is true that inflation ended in our part of the universe. But there are three concerns about which we are unsure of the answers and which have a significant bearing on the size of the universe and whether it is infinite or not. 1. How large was the post-inflationary area of the universe that gave rise to our intense Big Bang? 2. Is it true that the universe expands into the future in some areas forever according to the theory of eternal inflation? 3. How long did inflation last before it came to an end and the hot Big Bang that followed? The universe in which inflation took place might have been only a little bit bigger than what we can see. Every year, there can be indications of a margin to the area where inflation is occurring. The Google universe, however, might be many times bigger than what we can see. We might never know unless we get an answer to these questions. Aside from what we can currently observe, we have a strong suspicion that there are many other universes similar to our own out there, each with the potential for sophisticated life and the same physical rules, cosmic structures, and physical types. The bubble in which inflation terminated should also have a finite size and scale, and the biggest space-time being inflated should contain an exponentially huge number of such bubbles. The entire universe, or multiverse, if you prefer, is unfathomably big, but it might not be endless. Unless inflation really went on forever or the universe was created infinitely big, the universe should actually have a fixed size. The fact that we don't have enough data to provide a definite response to the question, though, is the biggest issue. We are only aware of how to access the knowledge that exists within the 46 billion light-years of our observable cosmos. If the cosmos is endless or finite, the solution to the most important issue may be encoded there, but we cannot access it well enough to know it. We won't stop having possibilities until we figure it out or devise a creative plan to expand what physics is capable of. What are your thoughts on the unobservable universe then? What lies beyond of it? The multiverse or nothing? How exactly do you define it? Comment below with your thoughts and let us know what you think. Also, don't forget to like the video and subscribe to the channel because doing so motivates us to continue producing excellent material for you.